In machine learning, we train models on sample data to simulate real-world processes like cancer detection or fraud prevention. Assuming the population follows a normal distribution, a good sample ensures better model performance. Normality tests help check if a sample or variable follows this distribution.
Welcome to Data Science Cheat Sheets channel, transforming lines into limitless creations. What is normal distribution?
The normal, Gaussian distribution is a symmetric probability distribution where most values cluster around the mean, with equal chances of deviating in either direction and fewer outliers at the extremes. The term Gaussian distribution refers to the German mathematician Carl Friedrich Gauss. Key characteristics of a normal distribution. Symmetry. The distribution is perfectly symmetric around the mean, median, and mode. All three are equal and located at the center. 68-95-99.7 rule. 68% of data falls within one standard deviation of the mean. 95% within two standard deviations. 99.7% within three standard deviations. Tails. The tails extend infinitely towards the x-axis, without ever touching it.
Why? Normal distribution is so important.
Checking if data is normally distributed is crucial in many data science and statistical analyses, because certain algorithms and statistical tests rely on normality assumptions. Many parametric tests require normally distributed data to produce valid results. When the data isn't normally distributed, these models might yield misleading or inaccurate conclusions. For machine learning models like linear regression or time series forecasting models, having normally distributed data or residuals ensures predictors behave linearly with the response variable. Error terms have constant variance and are independent of each other. Model predictions are more reliable and stable. Non-normal data can contain skewness or outliers, which can affect the accuracy of predictive models, especially sensitive ones like regression models. Statistical inferences, leading to biased estimated of parameters. Some machine learning algorithms, such as decision trees, random forests, are not sensitive to normality. However, feature engineering techniques such as principal component analysis or dimensionality reduction often assume the data is normally distributed to maximize variance capture along principal components.
How to check for normality?
To check the normality of a variable, various graphs can be used. We can visually see the normality by using plots, but graphs are not very accurate as statistical methods.
QQ plot plots. Two sets of quantiles against each other, that is, theoretical quantiles against actual quantiles of a variable. If our data comes from a normal distribution, we should see all the points lying on a straight line. A box plot, also known as a box and whisker plot, is another way to visualize the normality of a variable. It displays the distribution of data based on a 5-valued summary, such as minimum, first quartile, median, third quartile, and maximum. If your variable is normally distributed, we should see the mean and median in the center. One of the popular and commonly used graphs to visualize the distribution of data is the histogram. It also allows us to check the data outliers, skewness, and other parameters. It divides the data into bins of equal width. Each bin is displayed as a bar, and the height of the bar depends on the number of data points in that bin. If your variable is normally distributed, we should see a bell curve.
On the other hand, there are many statistical tests to check whether a variable is normally Gaussian distributed.
In this section, the Python code for each test will be shown. Let's start with the Shapiro-Wilk test. This is the most powerful test for checking the normality of a variable. It was proposed in 1965 by Samuel Sanford Shapiro and Martin Wilk. If the p-value less or equals 0.05, then we reject the null hypothesis. That is, we assume that the distribution of our variable is not normal. If the p-value greater than 0.05, then we cannot reject the null hypothesis. That is, we assume that the distribution of our variable is normal.
D'Agostino's k-squared test tests the normality of a variable based on skewness and kurtosis. It was named by Ralph D'Agostino. Skewness is a measure of symmetry. Kurtosis is an indicator of whether the data is heavy-tailed or light-tailed compared to a normal distribution. If the p-value is less than or equal to 0.05, we reject the null hypothesis, indicating that the distribution of the variable is likely not normal. If the p-value is greater than 0.05, we fail to reject the null hypothesis, suggesting that the distribution of the variable can be considered normal.
The Anderson-Darling normality test is another general normality test designed to determine whether the data come from a specified distribution, in our case, a normal distribution. It was developed in 1952 by Theodore Anderson and Donald Darling.
It gives a range of critical values at which the null hypothesis can be rejected if the calculated statistic is less than the critical value. In our case, at each significance level, the data have a Gaussian distribution. Another way to test the normality of a variable is to use the chi-square normality test. It is not as popular as other methods. The Lilliefors test is a normality test based on the Kolmogorov-Smirnov test. This test is used to check whether the data comes from a normal distribution. It is named after Hubert Lilliefors, a professor of statistics at George Washington University. A p-value less or equal 0.05 leads up to reject the null hypothesis, meaning the variable does not follow a normal distribution. A p-value is greater than 0.05 means we cannot reject the null hypothesis, implying the variable may follow a normal distribution. The Jarque-Barra test checks whether the sample data has skewness and kurtosis, consistent with a normal distribution.
Note: this test only works for a sufficiently large number of data sample, more than 2,000 observations.
When the p-value is less or equal 0.05, we can conclude that the data does not conform to a normal distribution. When the p-value is greater than 0.05, we assume the data fits a normal distribution.
The Kolmogorov-Smirnov test is non-parametric statistical test, used to determine whether a sample follows a specific distribution, such as the normal distribution. It compares the cumulative distribution function of the sample data with the cumulative distribution function of the reference. Theoretical distribution. The test calculates the maximum difference between the cumulative distribution function of the sample data and the cumulative distribution function of the normal distribution. The result is p-value. If the p-value is greater than 0.05, we cannot reject the null hypothesis, suggesting the data is consistent with a normal distribution. If the p-value is less than or equal to 0.05, we reject the null hypothesis, indicating the data is not normally distributed. The Kolmogorov-Smirnov test is sensitive to deviations in both shape and location of the distribution, although it may be less effective for small sample sizes or when data contains outliers.
These tests help you determine if your data meets the normality assumption, which is crucial for certain statistical and machine learning models.
In summary, checking for normality is essential because many statistical methods assume normally distributed data for valid inference, and some machine learning algorithms perform better with normally distributed features or residuals. Identifying deviations from normality helps make informed adjustments to analysis and model building strategies.
The code examples demonstrated in this video are at your fingertips. Simply check out the Jupyter Notebook linked in the description below to explore and experiment with them yourself. Thanks for being a part of our journey today. If you enjoyed the content, hit that subscribe button. By subscribing, you not only show your support for the channel, but also ensure that you never miss out on the exciting content we have in store.